Three equal line segments GH, IJ, and EF are parallel to AB, BC, and CA respectively. They all intersect at a point P within triangle ABC. If the length of AB is 15, the length of BC is 12, and the length of AC is 10, then what is the ratio of AH to HJ to JC? We can solve this question by first noticing that it involves similarities and ratios. From each set of parallel lines, namely EF and AC, JI and CB, GH and BA, we can deduce a pair of similar triangles. For example, since EF and AC are parallel, triangle BEF and triangle BAC must be similar. This is because their corresponding angles are congruent to each other. Angle B is the same because it overlaps, and angle E and angle A are congruent because they are corresponding angles, and angle F and angle C are also corresponding angles. We can use the same logic to conclude from parallel lines JI and CB that triangle IAJ and BAC are similar, and also from parallel lines GH and BA that triangle GHC and triangle BAC are similar. We're also told that the length of EF, IJ, and GH are the same. Notice that all three lengths are a side length of a smaller triangle, such as EF and BEF, that corresponds to a side length of the bigger but similar triangle, such as AC in this case, with triangle BAC. Since all three small triangles are similar to triangle BAC, maybe finding the ratio of each small triangle to the bigger triangle using the side lengths given can give us more information to help us find what we're interested in. Okay, so let's find that ratio. We let EF, JI, and GH be K, since we don't know what it is, so K is just a placeholder for that unknown value. Then we write out the ratio of each small triangle to the bigger triangle, like this. Now we plug in the values, divide by K, multiply the fractions with the denominator's smallest common multiple, which is 60, and we get the simplified ratio of 6 to 5 to 4. So now we have the ratios comparing the ratios of each small triangle to the bigger triangles. And upon inspection, you can notice an interesting equivalence. In specific, that EF over AC is actually equivalent to AH plus JC over AC. The reason why EF is equivalent to AH plus JC is because EF here can be broken down to EP plus PF. And since GH is parallel to BA and EF is parallel to AC, quadrilateral EPHA over here is actually a parallelogram. This means that EP is equivalent to AH. Similarly, on this side, PF is equivalent to JC. Now, you might realize that these two lengths, AH and JC, are two of the lengths that we're interested in, which means we might be able to make more equivalences with the other two ratios over here and change them to something that has the lengths that we're interested in. So for JI over CB, it's a bit different here. Instead of using the properties of parallelograms, we use the fact that the ratio of one side of the small triangle to its corresponding side of the big triangle can be applied to any pair of corresponding sides of the two similar triangles. This means that the ratio of JI over CB is the same as AJ over AC. And further notice that we can change the length of AJ into two of the lengths that we're interested in, which is AH plus HJ. So we're getting closer to finding the ratio of these three lengths down here that we're interested in. For the third ratio, it's the same logic as the second one. And you get GH over BA is equivalent to HJ plus HC over AC. Now we have these three equivalences that incorporate the lengths that we're interested in. We can replace the previous ratios with these. Okay, now notice that the denominators are all the same, so it cancels out. And now the only variables involved in the equation are the lengths that we're interested in. However, we want to isolate them, not have them added together, so we have to get rid of the ratio over here. And a good way to do so is to let the ratio between them be r, and you get these three equations. By solving these equations, we can find what AH, HJ, and JC is in terms of r, which we can then use to find the ratio between them. First, we can subtract the second equation from the first and get this. And this new equation is very similar to the third equation over here, and if we add them together, we can find that JC is 5 over 2r. Okay, so now that we have JC in terms of r, we just have to substitute it into the first and third equation to find what AH and HJ is in terms of r. Plug it into the first equation and we get AH equals to 7 over 2r. And we do the same to the third equation. And we end up with HJ is equal to 3 over 2r. Now that we know what AH, HJ, and JC is in terms of r, we can finally substitute it into the ratio that we're looking for, which is the ratio of AH to HJ to JC. Then we can divide by r, multiply the ratios by 2, and we get the final simplified ratio of 7 to 3 to 5. And we're done.